To start the day, we have an exciting workshop titled Measurement Using a Vector Network Analyzer, conducted by Sri Lakshmi Narayan T, Senior Lead Engineer, Technical Support at ANRITSU India Private Limited.
With a total experience of 15 years in RF testing and measurement instruments, Sri Lakshmi Narayan brings a wealth of knowledge to the session. He has been with ANRITSU India Private Limited since 2015 and has previously worked for 8 years at Agilent as a calibration lead and technical support lead engineer. His extensive expertise makes him perfect guide for today's workshop.
So let's give a big round of applause to welcome Sri Lakshmi Narayan T to conduct this workshop. Over to you, sir.
So good morning everyone. So my name is Lakshmi Narayan. I am working in ANRITSU India Private Limited as introduction given by your colleague. So I have experience of somewhere around 15 years in the RF field. So I worked in a CUSAT and ANRITSU right now. So today we will be working on, we will be doing a presentations on a vector network analyzer and some of the parameters or measurements we can do using a network analyzer. Okay. So everybody know about the VNA? So you have used the VNAs? Okay. So we will see how to use the VNA and what are the parameters we can do in the using a VNA and some of the measurements we will do in the antenna and the filters and amplifiers. We will explain how to do that characterization or a testing of the components, and we will cover some of the portfolio what is there in ANRITSU and what are the solutions we are providing to the market kind of thing. So we will do all the things in the around up to 12:30 kind of thing. Okay. So before that, let me introduce ANRITSU. ANRITSU is established in 1895. So we are having approximately 4,000 employees in the globally, and we are having 23 sales offices and R&D manufacturing about 8 sites worldwide. So we are mainly focused on test and measurement instruments, but we are some of the business in the inspection equipments and food products and information and communication equipments also. So this is our the ANRITSU, and we are having a manufacturing company in Japan and USA. So we will do some of the products in USA and some of the products in Japan, and we are having somewhere around 230 plus human resources in the India, which will be supporting for the customers. So we are well technical person or there's in the calibration and servicing lab, which they enable accredited lab is there. So where they will support to you for doing the calibration or repair kind of thing in the instruments. So we will support for all the educational DRDO labs and some of the aerospace and other segments also. So before starting with the VNA, we have to know what is the transmission line, some of the basics of transmission lines. So without knowing the transmission lines, we cannot go for the RF radio frequency range, and we cannot understand the VNA, what is the terminology, what we are telling. Okay. So before that, we will talk about or we will learn something about the transmission lines. So transmission line is the basic for the RF radio frequency. Okay. So there are different medias in the transmission line where we will transmit the signals, like coaxial, waveguide, coplanar, strip line, and twisted pair kind of thing. So these are the medias where you will be transmitting the RF signals or any signal maybe. Okay. So where it will be used, the microstrip and coplanar means whenever you are doing the printed circuit boards, you will be using a coplanar or a microstrip line. Okay. So the main fundamental for a transmission line is the characteristic impedance Z0. So that will be the main parameter for the transmission line, and which defines the relationship between the voltage and the current. Okay. So the function of the transmission, the characteristic impedance will be the physical dimension and dielectric constant of the media what we'll be using for the transmission, and we will be using either a 50 ohms or a 70 ohms in the circuit systems or a RF system. Okay. So 50 ohms will be used for the RF and other instruments or any RF circuit boards. We will be using the 50 ohms, and 75 ohms will be used in the, where you will be using 75 ohms? In the TV and broadcasting, we will be using the 75 ohms. Why you will be using 75 ohms? Any guess? So because the 75 ohms will be having a low attenuation or a low power, low attenuation. Okay. So for a low attenuation, we will be using the minimum loss will be there in the 75 ohms. So that's why we will use a 75 ohms as a impedance in the transmission of a cable or any broadcasting kind of thing, TV and broadcasting. Okay. And 50 ohms will be using for the, why we will use a 50 ohms? Because it can transfer a maximum power. Okay. Using a 50 ohms, we can transfer a maximum power with a low attenuation. Okay. So that's why we will be using a 50 ohms. So why the 50 ohms? Once again, so how we will do the 50 ohms actually? So we will calculate the dia of the conductor, outer dia and inner dia, by 135 by log d by outer dia by inner dia. So using this, we will do the calculation of the impedance. So when you calculate for a lower attenuation like 77.6 ohms, if you need, the dia will be 3.6 will be the characteristic impedance. Okay. So this is the calculation for whenever you are transmitting the lowest attenuation of the signal. And when you want to transmit a higher frequency, it may be somewhere around 30 ohms impedance, which will be transmitting the optimum power. Optimum power means the maximum power will be transmitted. So to compromise between the lowest attenuation and highest power, we will be using the 50 ohms. Okay. So between the 77 and 30 ohms, we will be using the 50 ohms for the maximum power transfer with the lowest attenuation. Okay. Now you got why you will be using a 50 ohms. Okay. So next we will go for the transmission line. So what happens the transmission line when we connect a short at the end of the transmission line? So we will transmit the signal, which will be 180 degree. And depending on the, when you connect a short, it is a purely the reflective element. So whatever the signal it will be transmitted from the transmitting end, all the signal will be reflected back. There is no signal will be observed in the short, and the same magnitude will be reflected back, but in the opposite direction. Okay, with a 180 degree out of phase when you connect a short at the end of the transmission line throughout any length of the transmission line. So it will be 180 degree out of phase when you connect a short. What happens when you connect a open? So you are transmitting a signal 180 degree, and depending on the characteristics of the short, and it is also a purely electric reflective element. So the signal will be transmitted back with the same magnitude, but it will be in phase. Okay. So when you connect a open, it will be in the in phase 180 degree, and when you connect a short, it will be the out of 180 degree. Okay. So what happens when you connect a load? So there will be nothing will be reflected back because it is matching the impedance. So whatever the signal is transmitted, it will be observed in the load. So nothing will be transmitted back. So this will be same for the long length or the kind of thing, any transmission line. And what happens when you connect a 25 watts or a 25 ohms of a load at the end of that transmission line? So the some signal will be reflected back. The 1/3 of the signal will be reflected back towards the source, because it is a 25 ohms resistor or a load at the end of the transmission line. So depending on the characteristics or the conductor of the load, the signal will be reflected back. Okay. So if it is a 50 ohms, it will be all the signals will be observed, and there will be nothing will be reflected back. Okay. 1/3 of the signal with a 180 degree out of phase. So anything doubt in the transmission line? So we will go for the network analyzer. So how many of you, whenever we think about a network analyzer, we will think of the network what we will be using Ethernet cables connected to the system and a PC, and we will test a Ethernet tester, or we will think about that way. But this is totally different network analyzer which will be used to measure the RF components, to characterize the RF components. Okay, and these all deals with the radio frequencies. So what is the frequency range of RF frequency range? Sorry? So you will be measuring up to somewhere around 26.5 gigahertz or 20 gigahertz. And what will be the millimeter wave range? Sorry? So you will be working in somewhere around 70 gigahertz, okay, 70, 100 gigahertz, it will be millimeter wave, and there is a different bands also. So when you go for the gigahertz, it works from some 70 gigahertz or 110 gigahertz. You can go up to 1.1 terahertz also, okay, depending on the communication and the applications wise. So now we are using a 5G at the RF frequency band, you know that, sub 6 gigahertz. And there is a one more band which works in the millimeter wave, which goes up to 38 and 39 gigahertz, 28 to 39 gigahertz. That is the band what we are working now in the millimeter wave. Okay, so what are the cellular phones you are using? It works in a sub 6 gigahertz. Maybe in the coming days it works in a millimeter wave band also. Okay, so this is about the network analyzers. A network analyzer is an instrument which is used to measure the network parameters in the electrical networks of electrical networks. The common will be the S parameters. What is S parameter? Scattering parameter. Why you will be using scattering parameter in the network analyzer? Any guess? Why are we not using a H, Y, Z parameters? Because this will be used for higher frequencies, and it is very easy to do the calculation or a further formats transaction we can do very easily in the scattering parameters, and it will be used for higher frequencies. When you go for a H, Y, Z parameters, it will be used for a lower frequency range. When you want to work with the higher frequency, we will be going for a scattering parameters. Okay, so mainly we will be working on the RF microwave measurements to characterize the active and passive components using a VNA, and we will do the magnitude and we will measure the phase measurements in the vector network analyzer. Okay, so for some of the parameters we need only magnitude, and some may require the phase information also. Okay, so if you have any doubts between the presentation, you can ask me between the presentation. Okay, so we need some of the both magnitude and phase for some of the characterization of the network, and phase and magnitude is required for both, for linear and non-linear device characterization for both. Okay, whenever you are doing the characterization for non-linear devices, we need both the information, phase as well as the magnitude. Okay, so which will give the better accurate kind of thing, the measurements, and it will give the designing efficient matching network information, and it can do the time domain characteristics also. Why users need a VNAs? To characterize the multiple instruments like devices in R&D, testing and testing devices in a manufacturing, and we need for a conformance test in the production to test whether the signal or the DUT is within the range. We will be using the network analyzers. Suppose you are a manufacturer of any components like any filter or antenna or any mixers, or you are doing some of the amplifiers also. So you want to test whether it is in the 1 dB compression point, what is the 1 dB compression point, or you want to do the VSWR or other group delay measurements. In that case you need the VNA to test that. Okay, so that will be configured depending on your connectors. what is the connector you will be using, like you will be using a coaxial or a waveguide, or it can be we can do the configuration depending on the DUT, like you are doing for an antenna measurement or a filter or a mixer measurement. So that depends on the ports. Whenever you are doing for a antennas, it will be for a 1 port, and whenever you are doing for a filters, we need a 2 port, and whenever you are doing the mixer measurements, we need a 3 port. Okay, so that depends on the component, and some of them depends on the materials also. So we will be doing some researches in the materials also, like solid, liquid kind of thing. For that, depending on the materials also, we will do the configuration of the VNA. What is the material type you want to do the characterization. Okay, so these are some of the examples where you will be using to the VNAs, and different configuration as done will be done. Okay, so S parameters, as I told previously, it will do the measurement of the transmission and reflection parameters. So it can do the gain compression. What is the gain compression? Where it will be measured? Any idea? So you have tested amplifiers. In the amplifiers, you will be doing the gain compression measurement, because when you are feeding the CW signal with the power, at certain level it goes straight and it will move linearly, and in the certain point it will drop. So the dropping point of 1 dB or a 3 dB point, we will call it as a gain compression. 1 dB point or a 3 dB point, that depends on the OEM or the end user who will be using the amplifiers. Okay, so that is called a gain compression, which we are using previously using a spectrum analyzer and signal generator we were doing. Now we can do using a VNA also, the gain compression point. Okay, and we have replaced some of the IMD measurements also, intermodulation, distortion, which we were doing using the spectrum analyzer and signal generator. We are doing with the VNA, and we are doing a spectrum analyzer in the same VNA, and we are doing some of the time domain measurement, noise figure measurement. This all comes under the component characterization, which we can do using a VNA with a traditional VNA. Okay, so some of the devices like amplifiers, filters, these are some of the components which we can do using a VNA. So VNA terminology. So as of now, there is any doubts to you? Okay, so now we will move to the VNA terminology. We will talk about the vector and scalar. What is vector and what is scalar? And we will talk about some of the passive and active components, and transmission, reflection, and S parameters, how we will be using in the VNA. Okay, so vector and scalar is nothing but the magnitude. You will get the only magnitude information of the DUT. So which we were using previously, somewhere around 1990s up to 2000, we were using a scalar network analyzer. Now the scalar network analyzer is no more. Now we are using a vector network analyzer, where we were getting the information of both the magnitude and the phase of the device. Okay, and passive devices are the devices which does not amplify the signal, and it will be like filters or attenuators or kind of cables kind of thing. And amplifiers are the devices which we apply a DC voltage, and the signal will be amplified in the output. So this will be the active devices, which will be the amplifiers, some of the active mixers kind of thing. Okay, where the major parameter will be the gain of the gain parameter. So transmission and reflection, the transmission parameters will be the insertion loss, gain, and transmission coefficient. So why we need to do the transmission measurement? To measure the strength, gain, or the loss of the signal. Okay, and we will discuss on what will be the transmission parameters also in the coming slides. And reflection parameter will be used to do the measure the impedance or a phase change of the DUT. Okay, majorly for a impedance and the phase change in the DUT will be using the reflection parameter. So that will be the return loss. Suppose any doubts as of now? Now you will go for something related to the network analyzer hardware part. Okay, suppose how it works. So if you take a device, so this is the device which will be any attenuator or any DIT. Okay, so we will transmit the signal, incident the signal to that, and some signal will be reflected back depending on the DUT characteristics. Some signal will be reflected back. We will label it as a and the incident will be the R. Okay, and some will be transmitted at the B. Okay, so these all related to the DUT. Some signal will be incidented, so signal will be incidented, and some will be transmitted, and some will be reflected back depending on the DUT. So depending on this value of R, A and B, we will do the network analyzer measurements. Okay, so the network analyzer measurements are done is the what we will do inside is the ratio measurement. Okay, so that will be the ratio measurement which will do the ratio between a reflected by incident, A by R. Okay, so whatever the signal, it will be reflected back A by R. It will be we will take it that parameter as a SWR, S parameters, reflection coefficient, impedance, admittance, return loss. This all comes under the reflection parameters, where you will be most often time you will be finding in the data sheet or in the VNA parameters. Okay, standing wave ratio, insertion loss and everything. So when you come for the transmission parameters, so this will be the transmitted signal from R to B. So the ratio between the transmitted by incident, and where you will do the measurement of a gain or a loss, S parameters, S11, S22, and transmission coefficient, incident group delay. This all comes under the transmission parameters. So depending on the material, what will be measuring between the two ports, will give the all this information. So what is the VSWR, return loss, gain, or S parameters, S12, S21, return loss, group delay, all those. So if you have any doubts in this or any questions? So this will be the major parameters kind of thing, or major information you have to know before using the VNA. Okay, what is transmission parameters, what is reflection parameters. Okay, once you know this one, you can do the any component measurements or characterization using a VNA. Okay, so next we will go for the next slide. We will be doing the S parameters. So the S parameters will be S11, S21, S12 and S22. So what is the now digits indicate, you know? The first digit will indicate the measuring port or a output or a measuring port. The second digit will indicate the sourcing port or a incident port, where the signal will be transmitted and where the signal will be received back. When you go for a S11, the signal will be transmitted in the same port and reflected back in the same port, S11. So that will give the measurement of the reflection parameters, like SWR or a Smith chart or impedance measurement can be done in the S11. And in the S21, what happens, it will transmit from the port 1 and received in the port 2. So if there is any DUT, there is a loss or a gain in the between the port 1 and port 2, it will give the gain or a loss. So that will be done in the, that will be called as a transmission parameters. Okay, S21 and S11, S11 and S22 will be the reflection, and S21 and S12 will be the transmission parameters. So whenever you are doing the measurements, you have to set the S parameters to S1 or S21 or S12 or S22 depending on your requirement of the device, or what are the characterization you want to do in the device. Okay, so this is how it looks in the VNA. You will get a S11, S12, S22 and S12. Okay, so we can set the one port S11 as an input reflection coefficient we can measure, and is in S12 we can measure the reverse transmission like magnitude and the phase, and in the S21 we can measure the magnitude and the phase as a transmission, forward transmission, and S22 will give the output reflection. So when you are connecting the input to the port 1 and output to the port 2, we can measure the output impedance, input impedance, and the frequency response, okay, in S12 and S21. So these are some of the parameters like input return loss, output return loss, insertion loss of the from port 1 to port 2 or port 2 to port 1. Okay. So any doubts in this? So you are doing any antenna designing kind of thing? You will be doing no antenna designs. So you will be setting some resonance frequencies also. So how you will do? You will do the simulation actually. So after simulation you will do the fabrication also. So when you are doing the fabrication, after fabrication you have to use a network analyzer usually. So when you are using the network analyzer, what are the parameters you will be measuring? Sorry? Okay. Standing wave ratio, SWR, and you will be doing some impedance measurements also sometimes. So how you will do the impedance measurement? So you will be using a log magnitude, or how you will do the impedance measurement? So you will be using a multimeter, VNA. So VNA, which graph you will be using for impedance measurement? Log magnitude. Okay. So log magnitude, if you go for a log magnitude, you will be using a real impedance. Usually you will go for a real impedance when in the graph type, whenever you are doing the impedance. Okay. And there is a one more way to do the impedance measurement. You can using a Smith chart also. Okay. So if you can see there is a straight line here. If the signal dot falls in between the center of the circle, it will be a 50 ohms. If the dot falls above the circle, it will be inductive, and if the dot falls in the down of the circle, it will be the capacitive. So these circles will represent the resistance and the arcs will represent the reactance by X parameters. Okay. So when you connect the short open at the end of the transmission line or a cable, the signal will be infinity, the impedance will be the infinity. When you connect a short at the end of the transmission line, it will be the 0. Okay. So the center line will represent the real impedance, and inductance and other things will give the reactance values. So using this also we can do the impedance measurements. Okay. And you use the polar display. So why you will be using a polar display? No idea. So the polar display will be used to do sometimes we will be using this for a radiation pattern measurement also, and a gain measurement also we can use. And this represents whenever the dots it will show it will represent the straight dots, it will represent the magnitude values, the magnitude of the signal. And these circles, it will show what is the phase. So at impedance, at what value the circle, your phase will be changing, it will show that. Okay. The polar chart will show the magnitude and the phase information you will give it. Okay. What is the degree of phase shift it is happening in the DOT. Okay. So these are some of the parameters we will be using in the tracers which will be used in the VNA. And there is a group delay also. What is the group delay? The rate of a change of a phase with reference to the frequency. So whenever you are transmitting the signal with a certain frequency, the phase also it will automatically change depending on the characteristics of the DOT. Okay. If there is a linear device DOT like amplifier or anything which is working in the linear region, you will get the display linearly. And if there is a non-linear device, there will be the group delay will be like this. So there will be a peak and there will be a distortion and there will be a peak. So this will be measured The group delay will be measured in mainly in the digital transmission systems. Okay, and some of the amplifiers also you will be using the group delay measurement to see the phase variation with respect to the frequencies. Okay, so you have any doubt in the measurements? What is the theoretical value of SWR? 1. And what is the return loss value of that? 40 dB. Okay, whenever you are measuring theoretically, it should be a 40 dB the return loss, and the SWR should be 1. But in the practical, it may not we can achieve the 1 dB 1 SWR, but it may be near to 1. Okay, and return loss also it will be less than somewhere around 40. If you expect in theoretically, maybe you can expect somewhere around 32, 20 or 15 also sometimes. That depends on your circuit or a component. Okay, but theoretically it should be 40 and the SWR should be 1. Okay, so have any doubts in this? Now we will move to the architecture of the VNA. This is a basic block diagram of the VNA, how it works and what are the components inside the network analyzer. Okay, so if you go for the network analyzer, there will be a source and there will be a switch and there will be a splitter. It is a switch with reference to, it is also a switch actually, it is a divider kind of thing, and there will be a directional coupler or a splitter sometimes, that depends on the frequency range, and there is a receivers. Okay, so this is the major block diagram of the basic block diagram of the VNA. So what happens when you are measuring the S11, the signal will be transmitted from port 1 and it will be transmitted to the source and it will be send a reference signal at A1. Okay, it will keep the reference signal at the A1 and it will be transmitted to the through the reflectometer like coupler, and it will be transmitted to the DUT. So whatever the signal transmitted from here, it will take this A1 as a reference and it will measure the reflected signal at B1 and the transmitted signal at B2. So whatever the measurement we will get when you are measuring, it will be B1 by A1. So A1 by B1 reflected signal S11 and B2 by A1 which is S21, which is a A1 by B2 by A1. Okay, you got it? How you measure the S11 and S21? So you will send the signal here, you will keep it this as a reference signal A1 and you will measure the reflected signal which will be the A1 S11, and we will measure the B2 by A1 by B2 by A1 which is called the transmitted signal. Okay, so this coupler will change, this reflectometer will change depending on the frequency ranges. For a higher frequency range we will use the couplers, so for a lower signal, for a lower frequency we will use the bridges kind of thing. Okay, and this will be similar to the port 2 also. The signal will be switched to port 2 and this will be the reference receiver, and this will be the reflected receiver, and this will be the transmitted receiver. So whenever you are measuring S22, the signal will be measured by B2 by A2 and transmission will be measured by B2 by B1 by A2 by B1, B1 by A2. Okay, so you will measure the transmission signal. So this is how it works, and this is a ratio measurement usually. So you have any doubt in the block diagram? So what is the spectrum analyzer measurement? It is what is the power you will be measuring in the spectrum analyzer? So in the spectrum analyzer we will measure the absolute power. Okay, and the network analyzer will measure the ratio power. So absolute power and ratio power. What is where you will be using a spectrum analyzer? What is the difference between spectrum analyzer and network analyzer? No idea. So the spectrum analyzer is used to measure the unknown signals. Okay, you can measure any signal. If you set the frequency range of the any frequency, suppose in the spectrum analyzer it goes from 1 Hertz to somewhere 20 gigahertz or 30 gigahertz or 43 gigahertz, we can set any frequency and measure the signal whatever radiated in the over the air, and we can measure the what is the level and what is the noise level or harmonics kind of thing in the spectrum analyzer. But in the network analyzer we will be measuring the known signals. Okay, we should know the what is the parameter you will be measuring and what is the frequency range of your device. Okay, so you will be measuring the known signals in the network analyzers. Unknown signal will be measured in the spectrum analyzer. Okay, so we can do directly connecting to the wire from the transmitter to the spectrum analyzer, and we can do the unknown signal measurement in the spectrum analyzer. But in the network analyzer we have to measure the known signals only. Okay, so you heard about the calibration. So why you will do the calibration? So the calibration will be why you will be doing the calibration? So as we know that this is a network analyzer or any RF instrument, it will be including the, as I told previously, it will be including the source, receivers and coupler, bridges kind of thing. These all components will generate some noise signals. Noise or there will be a phase variation and magnitude variation in the all these components. So, and whenever you are connecting the network analyzer, you will be connecting a adapter or a cable to the front end of the ports. So these all induce some noises and the magnitude and phase variations. To nullify that or to offset that, we will be doing the calibration at the end of the cable. Okay, to nullify or to offset to remove that errors, we will be doing the calibration at the end of the cables or the network analyzer ports. Okay, so there are two types of calibrations. So one, it is called as a instrument calibration, one is a measurement calibration. Okay, so what is instrument calibration means, which will be done every 3 years. Okay, it will be done every yearly, 12 months once. So how we will be doing the instrument calibration? We will do the certain parameter measurements using a enable accredited instruments. Using that as a standard, we will do the measurement or we will test the VNAs or any spectrum analyzer or any signal generator when you are doing the calibration. That is called a instrument calibration. Okay, and we will be talking about the measurement calibration also. This is be done for the VNA, as I told previously, to remove the error or to establish a 50 ohm reference at the output of the port, or to 0 dB or 0 degree at the end of the port. Okay, so this will be done. So this can be done using the two methods. We can do using a manual calibration kit, or we can do using a auto calibration kit also. So in the manual calibration kit, as we discussed in the previously in the starting slides, like a transmission, we will be using the open, short and load. Using these three standards, we will be doing the calibration. Okay, so that will be done in the mechanical calibration. And when you come for auto calibration, we will set an algorithm which will be known the cal factor of the instrument and the cables. That algorithm will be used to do the calibration, which will be done internally. Okay, so using a manual or a auto cal, we can do the calibration of the instrument. Instrument means it is a network analyzer. Okay, you have any doubts? So this is the method what we call, it is a short, open, load and through, SOLT and LRL. These are some of the calibration types which will be used in the VNAs. So who are using a VNA, they may be knowing this one, SOLT, short, open, load and through, LLR or SST, SSLT kind of thing. So you have done any waveguide calibrations also? In the waveguide calibration, we will set a different offset shots, and we will do the calibration actually. So there will be a different calibration kit for waveguide and different calibration kit for coaxial. Okay. So this is the calibration kit which will be including open shot load, male and female both. With the connectors it will be there. Okay. So whenever you are using a VNA, you should use a calibration kit with the cables. And the cables will be phase stable cables we will be recommending. Okay. Where you will get the better measurement. So why you want to do the calibration? Because this whatever the DUT measurement, we are measuring only the DUT. We are not interested in the cable loss or the instrument error, what will be there in the instrument or a cable. So to concentrate only on the taking only the measurement of a DUT, we have to do the calibration at the end of the ports, and where parallelly we will extend the reference plane up to the end of the connectors here. Okay. So it will give the only the information of the DUT once you done the calibration. So it defines a 0 dB and removes some of the systematic errors or frequency, load match, directivity, isolation. So these all comes under the components actually. What are the components it will be used inside the instrument. So that errors will be included, that will be removed when you do the systematic errors kind of thing. Okay. These errors will be contributed from the instrument. And random errors, which are some of the like connector stability or repeatability or environmental changes, these all occurs when there is a repeatability change or when there is a cable stability is change or is there environment changes. So these random errors may occur. This may not possible to calibrate out because it may change every time, but we can remove the systematic errors which is generated from the instrument itself, as I told. Okay, which will be contributed from the instruments. So these are some of the calibration types what we can do, like full two-port calibration, which will cover S11, S12, S21 and S22, and full one-port calibration, which will be S11 or S22 or okay, and we can do the one path two-port S11 and S21 or S22 and S12. Okay, so this depends on your component. We can select the calibration method. Suppose you are doing only for the antenna measurement and you want to do the only reflection parameter, you can select port, full one port calibration, and you can do the calibration for only one port. Suppose if you want to do the filter or any two port devices, you can select a full two port calibration and you can do the calibration for all the two port, and where you can measure the all the four S parameters. Okay. So any doubts in this up to this? Anything? So line reflect line, LRL. So line reflect line means you know the length of the connector, or if you are using a female to female connector, so you know the length of the line and you can enter the electrical delay of that line in the calibration method and you can do the calibration, and there is no need of a SOLT in that case. If you are using LRL, you can do the calibration using a line through, and the reflection coefficient, it may be any short or open. Okay, so you will be using only the short or a open reflection parameter or reflection standard, and you will be using only the through. Using those two we can do the calibration, and this will be not much accuracy when you compare to the SOLT, but it will do for a certain measurements we can do that. Okay, using a reflection standard and the line. Okay, line or a through, what we call. It is just nothing but the adapter, which is a known, which will be you already known the what is the length of the electrical length of that line. Okay, using that we can do that. Okay, anything else? And you are doing any test picture de-embedding, embedding kind of thing? Anybody? So embedding, de-embedding, heard about that one? So in the VNA, if you are doing any circuit board, suppose you are working in any signal integrity measurements or any in the high speed data, so you will be having a PC board and there will be a DUT between that. Okay, it will be in the center of the PC board. So you want to do the characterization of the DUT which will be connected between the PC board. So there will be a paths also. Okay, so you want to physically you should disable this path and you have to do the measurement, but physically it is not possible. In that case we can remove this whatever the circuit board in the simulation mode and we can do the calibration or we can do the measurement of that particular DUT. So that is called de-embedding actually. So physically it is not possible, but in the software de-embedding tool we can remove that whatever the test picture or any CRT board path and we can do the characterization of the modules. That is called de-embedding. And if there is any RLC circuit in the board, yeah, this, yes. So in the RLC circuit, suppose if you are having in the RLC components in the board, we can remove the RLC components also if you know the what is the value of the RLC. But physically we will not remove, but in the software we can remove the RLC component and we can measure the DUT. Okay, so in the DUT we can measure all the 4S parameters also. So that is that will be applicable whenever you are going for any industries or kind of thing, that will be used. Okay, so we can do the measurements of that using a de-embedding tools. Embedding means we will be inserting the RLC. De-embedding means we will be removing the RLC or any. Okay, and if you know the S2P file of that board, we can install or de-embed that file and we can do the measurements. So anything else? So anybody is working in the antenna also, 5G antennas, array antennas? No. Okay. Okay, we will have a break. So after that we will continue on the VNA, some of the device characterization and the portfolio of ANRITSU in the VNA. Okay.
Okay, now we will take a short tea break to refresh and recharge, and please be back in 15 minutes, maximum 15 minutes, and thank you and enjoy your break.
Okay, so now we will do some of the RF components or devices characterization and how to do using a VNA. Okay, so in the components we are having some passive devices, antenna measurement, filter measurement, active devices and amplifier measurement, and I will cover a VNA portfolio. Okay, so now we will do some of the passive devices. So passive devices are antennas, filters, cables, attenuators, bridges, combiners and splitters, etc. So this all comes under the passive devices. So mainly we will take it one antenna and we will discuss on that what are the parameters we will do in the antenna. Okay, so antenna is a device which transmit or receive the electromagnetic waves, which device the electromagnetic waves, and it is often referred to as a radio waves. Most antennas are resonant devices, so which will be operated in the narrow band where you will set the center frequency and we will be radiating the signal, electromagnetic signals, waves. Okay, an antenna is tuned to the sum of the frequency band as a radio system to which it is connected for either reception or a transmission. So there are different types of antennas like isotropic antenna which transmits every direction equally, and there is a dipole and monopole antenna which will be in the single element, dipole which will be two elements made up of two elements, and the array antennas which will be used in a set of antennas which will be used in the, where you will be using array antennas in a 5G. Okay, now whatever the 5G signal, it is using a array elements like array antennas, which will be focused to a particular location directional, and we will do the measurements, or we will transmit or receive the signal. Okay, and for a conical dish for a satellite and point to point radiation kind of thing, and for a beam forming you will be using a conical antenna, and some of the waveguide horn antennas are used for automotive applications, and from waveguide applications we will be using the horn antennas, which will be where we need a banded frequency range. So which works in the banded frequency range, we will be using the horn antennas. Okay, because it cannot cover all the bands, somewhere around 1 gigahertz to 50 gigahertz or 60 gigahertz we cannot cover in the horn antennas, it will be in the banded itself. So 8 to 12 like RF frequency bands. Okay, so these are some of the applications of the antennas which will be used in cellular communications, military, medical, LMR and WLAN and other things. These are some of the applications where we will be using the antennas. So what are the major parameters in the antenna? So we will be measuring the impedance matching kind of thing, which is called as an impedance measurement, and we will be doing the radiation pattern measurements and return loss and VSWR. So these are some of the major parameters in the antenna. What is radiation pattern means? You will be finding the gain of the antenna using a radiation pattern measurement. Okay, so you will get the information of the gain in the radiation pattern, and we will do the return loss for the measuring the resonance frequency. So suppose you are tuning for some particular frequency, somewhere around 2.4 gigahertz or 2.3 gigahertz, you are tuning the antenna, you can measure using the return loss, what we call, or you can use a log magnitude value and you can find out the what is the resonance frequency of your antenna. Okay, and VSWR we can measure, and we can measure the impedance using the Smith chart, or you can use a log magnitude and real impedance, we can measure the what is the impedance value of the antenna. Okay, so you can, we have taken example of one antenna which is resonating at 8 gigahertz. So these are when you connect to the antenna at the port of the port 1. So it is the antenna, it is a patch antenna which is connected, and it is resonated at 8 gigahertz. So when you connect this to the network analyzer, and if you are going for a S11 parameter, reflection parameter, so this will be the resonance frequency of the antenna. This is how it looks when you connect to the antenna. Okay, when you connect to the network analyzer. So it is having somewhere around 30 dB of the return loss. And if you are doing for a multi-bands, if you want to do the multi-bands resonance frequency measurement, so if you take example, we have done for a 1.8 gigahertz, 2.4, 3.5 and 5.4 gigahertz, the simulated value will be somewhere like this. It will be somewhere 1.8, 2.4, 3.5 and 5.4 gigahertz. This will be the simulated value. When you connect to the antenna network analyzer, it will be the similar kind of thing you can do practically. Okay, this is a simulated value you can do practically by connecting to the network analyzer. We can measure the same values, or you can check the simulated value compared with the real values. Okay, and when you want to do the radiation pattern measurement, so this is the setup what we will do. This will be the antenna under measurement, and this will be the isotropic antenna which will be connected. So this will be the golden standard, or it will be kept as a standard fixed kind of thing. And this will be the rotary, actually step motor kind of thing, which will be rotating in the different angles. And this will be connected to the one port to the VNA, and other port will be connected to the network analyzer. And this will be controlled from step motor and the turntable, and the software will be running through the PC. And this whole setup will be connected inside the chamber. So why you will be using a chamber for radiation pattern? Yes, to isolate the radiated signal from the outside the area. So the signals will be isolated from the outside the area, and it will do the measurement what is required to us. Okay, to isolate the signals. So it will be done inside the chamber. So this is the setup what we will do for the radiation pattern. So any doubts in the antenna, you are need any information related to the antennas, or if you have any doubts in the antenna measurements and designing part. Okay. So now we will go for the filter measurements. So these are some of the filters what we'll be seeing in the labs and other industries or any circuits. We will be seeing these band pass filters, low pass filters, band reject filters. This will be used. It will be done depending on our applications. We can select the particular frequency ranges, or we can stop the frequency range, or we can allow that particular frequency ranges. Okay. Where you will be using the band pass filter, you have any idea? When you will be requirement of a band pass filter will be there? So suppose you are transmitting some signals in particular bandwidth in the transmission, like any communication, wireless communication or any communication. So you will be transmitting some signal in particular bandwidth. So if you want to transmit that signal, you have to avoid other signals. So you will be only concentrating on that particular bandwidth. Okay, in that case you can put a band pass filter across the transmitter, after the transmitter, and you will be transmitting in that particular frequency. Okay, so this will be used, band pass filter. Okay, and when band stop will be used in the opposite side, in the receiver side, where you want to receive the particular signal itself. Okay, so other signals will be isolated. Frequency band will be isolated. Okay, some of the applications we can make n number of applications where the filters will be used. So there are different types of filters, and filter is a key component, as I told. Fiji commercial applications like military, aerospace, in satellite communications we will be using this, and in the wireless communication signals. So these are the parameters what we will be measuring in the filters. So we will measure the return loss, input impedance on the input side, port 1, and we will be measuring insertion loss, group delay, rejection in the transmission parameter. And when you come for a S22, we will be measuring what is the Q factor and shape factor at the other things. Okay, so this is about the filters what we will be measuring in the VNA. Okay, these are some of the parameters. So when you come for the insertion loss, we can do the insertion loss, and out of band rejection is nothing but the isolation. You heard about isolation in the filter? Whenever you are going through some of the data sheet of the filters, you will find out this out of band, or isolation, or insertion loss, and what is the noise floor of the instrument. You will get all this, the frequency band also. So what we called as isolation, the difference between the peak to the noise level. So this is called as an isolation, or the band stop, out of band rejection kind of thing. Okay, and this is the return loss when you connect a filter. This is the band of the filter, and this will be the response when you do in the return loss measurement. Yes. Okay, that is related to there will be a causes of 2 actually, that may be generated by the VNA itself. Sometimes when you are not doing the correction or calibration properly, you will get that noise levels. Okay, and sometimes that may depend on your DUT also. So before connecting to the DUT, you have to cross check to connecting it through between the ports. Okay, 2 cables you have to connect it through, and we can we can check whether the signal is purely a straight line, or without a noise it is there a straight line. Okay, and still you are facing the noise level, you can go for averaging or smoothing option in the filter or in the network analyzer, and you can nullify that noise level. Okay, so this is the band pass filter where we can do the center frequency, and you can find out what is the center frequency, low frequency, high frequency, Q factor, and you will get what is the loss of this, and what is the shape also. So this is the one button option in the shock line VNA. Using that shock line VNA, we can find out all these parameters in the single button. Okay, you can measure what is the 3 dB filter bandwidth also. Okay, these are some of the advanced features which is available in the VNA. Okay, so you will find out the what is the 3 dB bandwidth and 60 dB bandwidth, and you will get the shift factor and what is the value directly in the shock line VNA. So when you want to see the different traces, suppose I am seeing the log magnitude and I want to see the S11 and S21 both simultaneously, I can see that also, which will be very useful when you are tuning the filters. RLC component of the filter, if you want to tune, you need to see the both the traces in the single display. So this will be useful, and you can characterize the some of the parameters in the other trace S21, and you can see the S22 what is the value. So you can see all the 4 traces in the single display. You can get the impedance values, output impedance, or you want to do the frequency response and you want to do some simulation kind of thing. You can add one more trace. This can go up to 16 traces. We can set it in the network analyzer with the different parameters. If you want, you can keep it for one as impedance and one for the VSWR and one for return loss. You can keep it up to 16 traces in the single display, and you can analyze simultaneously. Okay, so there is one more option which we can set the frequency setup also. Suppose we have done the calibration up to you can see 1.4 to 2.4 gigahertz. I can make a segmented frequency sweep also, and I can find out what is the value of the return loss on that particular frequency segments. So I can make a part by part, and I can analyze the signal for the every frequencies. Okay, and I can set the limit for that, and I can check. So this is about the filters actually. If you have any components or you want to do the characterization, please let me know where I can help you out, except antenna or a filter or any other components. Any passive components or active components, you may ask. I can help you out how to do the characterization, or want to do the testing kind of thing. Observers, usually observers will be, observer means you are telling about the chamber, mixer kind of thing, surfaces. Okay, for that we are having some material measurement test fixture is there. Using the test fixture, we can do the observers material measurement kind of thing. So what happens, we will do the calibration at the one port, and we will connect the once we have done the calibration at the end of the port, we will connect your observer and we will do the S11 reflection parameters on that. Okay, and if you need both the transmission and reflection, we can do both the 2-port calibration, and we can connect the observers between the 2 cables, and we can do that. So where it will be used actually, tell me. It is, you are telling about which observer? Surface, no? Surface. So that's why over the here we can connect the observers at the one port of the cable. Okay, or you can place that observer between the cable, between the 2 ports. You can connect a horn antennas. Okay, and you can measure the what is the isolation, or you can measure the parameters. So you can place it between the 2 horn antennas. Okay. So this can be done in the uncoiled chamber. Okay. So if you need a more accuracy, and you are telling about if there is any environmental changes or it will make interference to your measurement, in that case you can do this in the uncoiled chamber kind of thing. With depending on your material, we can make the chamber. Okay. Yes, we can do that one. So if there is any sheet kind of thing, you can do a transmission method actually for the measurement.
Sir, can we use the non-linear behavior of active components?
Sorry?
Non-linear behaviors of active components. Can we use another devices for that? Measuring.
Any device, non-linear device also, we can do the parameter measurements. Okay. So any non-linear devices, linear and non-linear devices, both can be, we do the S parameter measurements.
Okay.
Okay, we will be coming in the active devices, what is linear and what is non-linear devices, and what are the parameters we will measure in the non-linear devices also. Okay.
Okay. Okay.
Array antennas. So array antennas, we cannot do set of array antennas, the calibrate the measurements cannot be done, but we can do individually. Suppose if you are having somewhere around 12 antennas, array antennas, we can do that using a switch box. So we will connect the network analyzer test port to the one of the input of the switch, and we can sweep from multiple switches up to 12 switches. Okay, more than that means we cannot do that one. We can use an individual port measurements kind of thing. Okay. So anything else? So we will go for the next active components, how we will do the active devices and how to do the measurements. So now we will take it example of, so these are some of the active components like amplifiers, mixer, transceivers, converters, transceiver modules and receivers. These are some of the active components usually we will be seeing in the RF. So this is a linear device. As we know, the linear device will be the input and output will be the frequencies are same, but the amplitude and the phase will change linearly. Okay, when you come for the non-active non-linear behavior, the output frequency undergo frequency shift. There will be a shift in the frequency, and this, depending on the DUT, it will create some harmonics also. Intermodulation and harmonics will be created. So you want to characterize this both the information, linear devices and non-linear devices. For non-linear devices, we need the phase and magnitude values both. Okay, but for the linear, phase magnitude is sufficient. Okay, so that's why we will be going for a network analyzer, vector network analyzer. Before that, we were having a scalar network analyzer which was doing only the magnitude. Now whatever the network analyzer is, it can do both phase and magnitude both. So non-linear devices, if you are having amplifiers which is having a non-linearity for certain region, after a certain region, so in that case you can do the return loss impedance measurement, gain compression, group delay, and noise figure measurements also can be done. What is noise figure? Okay, so we will come to know next. Okay, and there is a output matching also. You can do the input output impedance kind of thing. You can do the measurement, and you can do the some of the output power measurements, distortion, harmonic, intermodulation, isolation parameter. These all parameters covers in the amplifier. Okay, so we will know how to do this one. If you want to show the gain and input match, you will be doing the gain by using the S21 parameter, input match in S11 and output match in S22, and isolation can be measured in S12 also. Okay, so you can make the resonance frequency response measurement in S21 or S12, and input and output impedance can be measured in the S11 and S22 respectively. Okay, so this is the VNA. When you come for a non-linear measurements, we can do the IMD measurements. Usually what we will do the IMD measurements, we will be generating a two tones. Okay, you will be feeding to the input of the amplifier, and you will be measuring at the output if there is, depending on the characteristics of a DUT, any amplifier or anything. So it will create some harmonics also. Okay, two tones will be generated. So we will check at the output what will be the strength, what will be the level of the output of the harmonics with respect to the fundamental. As we know, this should be not much, it should be not equal to the fundamental whenever it is created. So to check this one, we will be using the spectrum analyzer and signal generator. Previously we were using a two signal generators. Now the ANRITSU VNA or any VNA, advanced VNA, there will be having a dual sources inside the VNA itself. So that will generate two tones, and using an internal combiner of the VNA, we can combine the two tones and you can feed to your DUT or an amplifier, and you can measure these characteristics. Okay, this is the one of the measurement what we will do in the amplifier or any active components, IMD measurement. Okay, so we can do that by we are having individual sources, and for these sources there is no, we will do the calibration at to the end of this cable, and we will do the source calibration at the port 1 and port 2, and we will do the receiver calibration using a path, and after that we will connect a combiner internally and it will be fed to the DUT. Okay, so any doubt in IMD? So this is the setup what we are having internally. So we can set the CW frequency, and we can set the two tones with the different frequency offset values and with the different power levels, and we can feed to the DUT. These are internally two sources and combiner, and it will be fed to the DUT. So this can be receiver, we have to set the what is the receiver value, we have to see. It will be connected to the other port of the VNA itself directly, and we can measure the receiver also. Okay, so it will act as a spectrum analyzer inside the instrument. Okay, because you want to do the intermodulation distortion, means intermodulation distortion is nothing but we have to insert a two tones with a nearby frequency. The offset value will be somewhere around 10 kilohertz. If you take as a 1 gigahertz as a center frequency of the any frequency, the working frequency of amplifier, so you will be generating two tones with a 10 kilohertz offset, and we will be seeing whether in the 10 kilohertz if there is any signal is generated, and it may affect your next future. Suppose you are implementing that amplifier in a transceiver modules, and there will be a band, that band should not interfere to your other bands. Okay, and how it will be affecting your fundamentals. For testing in the future transceivers or any modules, we will be testing the each components here itself by feeding the nearby offset of somewhere around 10 kilohertz offset kind of thing. Okay, so now we are feeding up somewhere around, we can set for 15 kilohertz, or this is up to 15 kilohertz we have set here, offset of two tones, and we have generated two tones, and we are using a combiner we have fed, and we are be analyzing in the same signal network analyzer the output of this one. Okay, so this is a software kind of thing which is having in the internally in the spectrum in the network analyzer itself. Okay, any doubt in the IMD? Next we will go for the noise figure measurement. So noise figure measurement, where there is a two types of noise figure measurements, which will be using a hot cold methodology and a cold source methodology. So hot cold methodology, we will be using a noise source, and we will do the noise figure measurement of the any active components like amplifiers, attenuators. We will see the what is the noise level of the components. Okay, so in this cold source method, we will be using the connecting amplifiers and band pass filter as a reference, and we will do the receiver calibration, and once we have done the receiver calibration, we will connect a load, and we will measure the what is the total noise level in the instrument with the components using a noise power calibration. And once we have done the noise figure calibration, we will connect a DUT between the load and the noise figure, whatever the offset, reference offset, and we will do the noise figure measurement. So this will be done. Okay, and there is a, as I told, there is a two types. You can use a noise source also, or internal noise also, you can choose it. Pulse width parameters, you heard about this one? So this will be used for a transceiver modules which will be used in a radar applications. Suppose your modules are radar application kind of thing, transceiver modules. In that case, you will generate some pulsed signals to your module, and you will characterize the S parameters and the output. So you will do the S parameter measurements by generating or by transmitting the pulsed signal to your DUT. Okay, so these are some of the parameters. We will generate a pulses like overshoot, peak power, average power, rise time, fall time. These are the known characteristics of the pulses. Okay, so you will measure the what is the rise time, fall time in the output of the signal. Okay, delay and other things. These are the parameters actually for a pulse characteristics. So there are two types of stimulation we will generate. We can generate the pulse profile. Pulse profile means it will give all the information. As I told, the pulse characteristics can be measured in the output of the DUT. and we can measure the point in pulse. We can see the pulses points also. We can set a different points here in the input, and we will measure the same in the output of the pulse. Okay, and will be doing the pulse to pulse measurements also. Pulse to pulse, you will be generating a bursty pulses at the input, and you will be seeing the what is the difference in the output, whether the interval between the pulses are same or it is changed in the output of the pulse. Okay, so these are some of the three tones will be generated, three pulses will, the different configuration will be generated in the port 1, and it will be analyzed in the port 2. Okay, so this is called a pulse DS parameters. So we can generate up to 4 single, doublet, triplet and quadruplet and bursty signals, bursty pulses, and we can do the characterization of the device. So it is having a high resolution and independent measurement results. Now we will come for the O2E, E2O electrical optical measurements, electro-optical measurements. So some of you are any working in the fiber optical instruments? Nobody is okay. Okay, so there will be a photodiodes. You heard about a photodiode, which will convert from electrical to light. Okay, and there is an optical modulator also, which will be modulating in the optical, and some laser light is there. Okay, so to differentiate, to characterize these components also, we can use the same VNA. So the same VNA can be used to characterize these components also, photodiode or a mode of optical modulator or laser diode, laser. These all can be characterized using the same VNA. So what happens usually? So we will do the calibration up to the end of this port. As we know, port 1 and port 2, it will be calibrated, and we are having some known photodiodes. Okay, using this photodiode we can do the characterization of these two. So first we will do the we know the value of this one. Okay, this calibration coefficient of this photodiode. So you will de-embed up to this point, and we will be already calibrated this point. So we will do the connect the between these two ports, we will connect the photodiode and laser, and we will do the characterization of this one. Okay, when you want to do the characterization of photodiode, we are having a standard optical modulator also. Using the standard optical modulator, we know the value of optical modulator, we will do the characterization of photodiode. So it is vice versa. We are having both the things as a standard, photodiode and modulator. So keeping that as a de-embedding the photodiode or optical modulator, we can do the characterization. If we are having both the things, we can do the characterization of this fiber also, optical fiber also. Okay, so that's why we can do the de-embedding and we can do the characterization of any components. Okay, so any applications or any components, you have doubt in any measurements or anything? So now we will go for the VNA portfolio. What are the solutions we are having in the ANRITSU to do this all the measurements and different types of instruments what is available in ANRITSU. Okay, so we are having a VNA with the different frequency ranges, and we are having a VNA depending on the ports and port product kind of thing. So if you go for this, we are having a handled VNAs, starts from 5 kilohertz to goes up to 40 gigahertz. We can do all the 4S parameter measurements. Okay, and we are having a shockline VNA, which is a USB kind of thing. So just a plug and play instruments are there, or the CPU will be inbuilt on these instruments, 2 port and 4 port. Using this we can do the active measurements also. Okay, and this is for a passive component measurements. We are having a USB plug and play, and USB, the CPU and the software, it will be inbuilt in this instrument. We need an external display. Okay, so these are some of the VNAs which is available in ANRITSU. So depending on the application frequency range, we can select the VNAs. We are having one port VNA also. Why you need one port VNA? because to do the antenna parameters S11 measurements. Okay, so why you want to for 2 port? When you are using, you want to do the antenna characterization, 1 port is sufficient, except when you are doing the radiation pattern measurement. For just for verification or testing the antenna, 1 port is sufficient for the antenna, for the VNA for an antenna. Okay, so this 2 port and 4 port will be used whenever you want to do the mixer measurements. Okay, when you are doing the mixer measurement, you require a 4 port, because you will be 2 will be the sourcing and 1 will be the analyzing. Okay, so we are having up to 43.5 gigahertz, starts from 8 gigahertz the starting frequency, 4 gigahertz for a single port, and 2 port it will be 8 gigahertz to 43.5 gigahertz. Okay, so in this there is no power sweeping of these instruments, and in this there is a power sweeping. Why you need a power sweeping? Because this is a ratio measurement. Okay, you know the power, so you anyhow you will do the reference, you will take as a one as a sourcing port power as a reference, and you will do the ratio measurement. But you need a, why you need a power sweeping? For which component testing we need a power sweep? Whenever you are doing for amplifiers, you need a power sweep. Okay, so when you want to do the gain compression measurement or frequency response of the power amplifier, you need a power sweep. So you will be setting one as a CW frequency, and you will be setting a start and stop power, and you will be sweeping the power at particular frequency. It will start drifting down. So in that case you will measure the gain compression point. Okay, for amplifier we need a power sweep. Suppose if you go for a VNA, there will be having some damage level. It will be having some plus 23 dBm, the damage level of the input port. So when you want to do the amplifier measurement, the gain of the amplifier, it will be somewhere around 30 dBm. So in that case what you will do, you have to connect a attenuator. Okay, attenuator at the output of the power amplifier, and you want to do the measurement. Be careful whenever you are using a attenuator, what is the damage level of the input port of the network analyzer before connecting the active components. Okay, so you have to take care of that. Okay, and we have got some newly launched phase link distributed VNA. Okay, so what is this application new term? Let me go through that. So this is about that. So what happens when you are doing the measurements? If you are doing, there is a application where there is a long cables, somewhere around 1 meter, 2 meter is a little bit less. When you go for the ships or a big chambers or flight aircraft, there will be length will be different, which there will be connected. One antenna will be connected at the wings of the aircraft, and other antenna will be connected at the head of the aircraft, in the front end of the aircraft. So there will be long cable laying between the connectivity from tail to the, or a tail or a wing to the whatever the front end of the aircraft. In that cables there may be somewhere around 100 meters or 50 meters, 200 meters kind of thing, the length of the cables. As we know, when the length of the cable varies, the loss also varies, increases, no? For every meter of the cable there will be a loss, some 0.5 dB. It will almost increases the loss. And when you go for the longer cables, there is a issue of the phase also. Whenever you are doing the measurement of the magnitude and the phase, if the phase varies, when you move the cable, automatically the phase also varies. Okay, so this is the issue what we are getting in some of the measurements in the long cables. Length of the cable, it will be affecting the phase and the loss of the cable. As we know, you can see here, if the coaxial cable is having a phase change of somewhere 4 meters with the temperature, it can go in the 40 gigahertz, it can vary somewhere around 120 degrees kind of thing. Okay, And in the loss, you can see there is up to 40 gigahertz. We are having a loss of somewhere around 12 dB the loss of the cable. So this is the major issue what we are finding in the long length cables actually when you are doing the S parameter measurement. For this we have a solution which we call it as a phase link technology. Actually what we did, we have taken a 2-port VNA, one single port VNA, and we have connected one more single port VNA, and we have extended these cables, whatever the controlling unit, we have extended the cables up to 5 meter, 50 meter, 100 meters directly. So these are the cables which will be connected directly to the network analyzer, and this port will be connected to the DUT directly. So there is no need of any other cable. This cable what we have supplied now, this is a phase link cable which will take care of the phase and the magnitude both. So there will be no changes in the phase and magnitude. This network analyzer, whatever the port is there, it will be extended to the up to the end of the DUT directly. So now you are eliminating the cable. So we are connecting directly the head of the ports of the cable and network analyzer to the instrument itself, the measurement DUT. Okay. So whatever the length of the cable, 150 meters or 100 meters, that will be the electrical phase link cable which will be supplied from the ANRITSU. Okay. So these are the cables. So this is a 5 meter actually. This will be up to 300 meters we are having a solution. This cable. This will go directly to the one end to the tail or the wing of the aircraft, and one will be connected to the front end of the aircraft, and we will measure the S parameters. It will give the information of both phase and magnitude. Okay. So let me show you some of the examples also. It is having, we are having up to 8 gigahertz, 43.5 gigahertz, VNS kind of thing. This is the, what is the configuration which will be connected to the PC. So this is one of the application where you will be using the, it will be used in the chambers actually. So in the chambers also you will use the network analyzer, which we were using signal generator to amplify the signal at the one end, and the length of from ear to the ear, it will be somewhere around 100 meters or 50 meters, the long distance between the antennas. So one will be connected here. This is LO, IF and other things which we were using previously. Now ANRITSU has made directly connect antenna here and one antenna here, and the VNA port will be directly connected here itself. So we have reduced the setup with the price also, cost also. Okay. So this is one of the application in uncoiled chamber actually for a near field and far field antenna measurements. And this is the one more thing as I told now. So this is the setup what they were using previously. They are using signal generator amplifiers and connected to antenna, and they are transmitting through over the air, and they are receiving using a mixers and down converters, and they were measuring the VNA port, other port. Now we are done directly, we are connecting the antenna port to the network analyzer directly to the antenna. Okay. So this is one of the application. And for the large vehicle, suppose as I told, the aircraft or a jet, there will be one antenna will be connected here and other antenna will be connected here. For this also we can use the same. And when you go for a ships, the antenna will be here, the controller, the base station will be somewhere inside the ship. So we can do the antenna characterization by connecting like this. These are some of the application where it will be used. This is a tail and this is front end. Okay. This is the, what was the older setup what we are using a 2 benchtop VNS, and we are connecting the one antenna here and one was inside the antenna. This is very bulky and costly solution. So we have made it as simple as possible. Okay. So this is an automotive application where we will be connecting one within the high arc, and it will be turning the vehicle. We will be measuring the what is the loss or the gain. Okay. Antenna measurement. So these are all related to the configuration. I think that is not required to you. So you have any doubt in the distributed VNA? Any doubts or any questions related to that application or anything? How it works or any doubts are there? We can use up to 300 meters length cables. Okay. And we can do the measurements on that. So this is about the vector star what we are having, high performance VNA. which is used in most of the RF DRDO labs and in the calibration centers. In VSSC we are using the here in Trivandrum. They are using this as a calibration asset and they are doing the calibration of the components. And this will be used in a DRDO, BL, Bharat Electronics and LRD. In the many other high performance for testing of the components, they are using this VNA. Okay. So this starts from, we are having a different modules kind of thing. We can extend this 2 port to 4 port and we can do some of the, as I told previously, we can do the IMD measurements, pulse width parameter, noise figure measurement and spectrum analyzer. Now we have inbuilt it in this instrument up to the 70 kilohertz to 220 gigahertz. Okay. So it is having a solution of 220 gigahertz single sweep, 70 kilohertz to 220 gigahertz. Okay. So this is a setup. If you are working up to 1.1 terahertz, we have to add 2 modules which can extend up to 1.1 terahertz also. Where is the application of 1.1 terahertz? On wafer measurements we are using 1.1 terahertz and some of the materials or components in satellites they are using 1.1 terahertz. Okay. In the some of the labs, they are in the research labs, they are researching on 1.1 terahertz in the materials. Okay. So this will be the fixture and the connecting tip which will be connected directly to the board or the DUT inside this board, and it will do the characterization of the component. It will measure all the 4S parameters also. Okay. So vector style we are having up starts from 20 gigahertz, 70 kilohertz to 20, 40, 70, 70 gigahertz we are having the instrument 2 port VNA, 4 port VNA, and 110, 120, 145 and 220 we have to use external modules kind of thing, which is a ANRITSU modules, and we can extend up to 110, 125, 145 and 220 gigahertz. Okay. It is a single sweep from 70 kilohertz to 110, 125 or 145 or 220. We can sweep in a single sweep 70 kilohertz to 220 gigahertz. And suppose we need to extend that up to 1.1 terahertz, we will be depending on this VDA modules. So this VDA module works in a bandits actually. So it works from 140, 220 to 300, there will be a one band, and 300 to 400 or 600 there is a one more band, and 550 to 750 there is a one more band, and 750 to 1.1 terahertz there is a different band. So this all works in different bands actually, the VDA modules. Using that we can extend up to 1.1 terahertz, but it will be a module solution, banded solutions. Okay. Up to 220 we are having a single solution. So this can be work up to 2 port or a 4 port also. So this can do all the 4 active component measurements, passive device characterization we can do, millimeter wave and frequency translation, embedded or radar, signal integrity, antenna. These all the parameters can be done in the vector star. Okay, it is complete solution, and the cost also it will be more. Okay. So any doubts? Yeah, it will be resolution will be less, and that depends, it will be not in the VNA side, it will be in the video module cap specification. Yeah, that will be having the particular band. So it will be having a already band. So suppose you are up to 220, so it will be having a band somewhere around 250, 210 gigahertz to 350 gigahertz. There is a one band. So in that particular band you can see, you can sweep the frequency in particular that band, and we can do the S parameter measurements. If you want to work with a 550 or a 450 gigahertz, you have to purchase 300 to 600 550 gigahertz ka band, one more, and we have to see that particular band. So it is a banded kind of thing. There is no continuous sweep from 70 kilohertz to 550 or 600. So it is a banded. Okay. So what? Sorry? 1.1 terahertz. 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 1.1 t Submarines. Submarines, there will be, you want to do the characterization or how it will be working, you are telling?
How about, you told about the aircraft and all. So how it is working in the submarines?
Aircraft, it will be doing in the over the air. When the antenna, it will be already, it will be installed in the submarines actually, okay. So the cables, it will be not corrupted because they will be making the purely safety on the cables or antennas what will be connected in the submarines actually, okay. Before installing that, we will do the testing of the submarine vehicles kind of thing, okay. After doing the parameter testing and other testing of the antennas and cables, we will install it and we will leave in the submarine, okay. So before installation, we will do the everything and we will install the cables or antennas in the vehicles. So 220 gigahertz, you are telling about 70 kilohertz, starts from 70 kilohertz. That depends on the frequency range. If you go for just a normal box with a S parameter measurement up to 220 gigahertz, it may go somewhere around 4 to 4 crores, 4 CR. Okay.
You directly connected the antenna, the VNAs with the DUTs. So, but in the actual aircraft, they will be connected with wires. So, the phase drop and the signal drop will be still be there.
No, this will be related to the cable test. That's it. Okay. This we will be doing only the cable testing, whether the cable is healthy or not, or is there any parameter variation, we can check in the cable. So, okay, once the cable is good, it can do the performance. You can take a 100% performance. There will be no attenuation or a loss in the cable or a signal when you transmit from there or controlling from here to there. There will be no loss in the signal. Okay. So you will be testing the healthy condition of the cables or antennas what will be mounted in the aircraft. Cable and antenna.
Feedback of that. So we'll do the traditional method. This is a new new methodology that we have invented. So we are segregating two ports of VNA. One we are connecting the other end, and one is one will be transmitter. One port will be receiver. So we are configuring it as a complete two-port network analyzer. So it will send out the signal at the other end of the cable, and other end of the cable the response will take it back and it will give it to the VNA. Instead of terminating, we are connecting one more port, the receiver port itself. So the accuracy will be more. So generally, if it is in open condition, like a 10-meter cable before lying in aircraft, so it is in the integrated stage, no? Yeah. So what you do, you can bring both the end of the cables to the VNA. One port will be connected like a transmitter, and other port will connect to the port 2. So we'll send out the signal and we see the response and we see the losses. Say suppose you are sending 1 dB signal at the end of the cable, after 10 meters, what is the loss of the signal? Like you are getting 0.8 or 0.7 or 0.5 dB. So you'll see that 0.5 dB is the loss for 10-meter cable. So in aircraft or any ship, no, the cable is already routed in the aircraft. You can't bring the both ends to the VNA. In that case, what we are doing using this distributed VNA, we are connecting both ports, so like one will be here and one will be other end of the cable. So we are configuring it as complete two-port network analyzer. So that way we are analyzing the cable losses. Similarly, antennas also, like one antenna will be here. This will be my transmitting antenna, and other antenna will be somewhere other like a second floor or the fifth floor of the building. So you are transmitting from signal to the antenna. So generally what you have to do, you have to characterize the losses between the two antennas. No, you have to bring both the ports to VNA actually. So one will be a reference signal in and reference out of the, you have to bring it to the VNA. So you don't have provision to connect those two antennas, no, because it is long distance, like 10 meter, 20 meter, or 30 meter away. In that case, no, the transmitting antenna, we are connecting one port of the VNA. For the receiving antenna, other port of the VNA, we are connecting directly to the DOT, and we are bringing back that response to the controller, so that you will see the characterization of the antennas also similarly, like that. Yeah. This is for long distance, like that. If you take ship, no, it is like a 3-storied, 4-storied, no. The somewhere in antenna to control room, there is a long distance cable, 200 meter, 300 meter. So to see the condition of the cable, no, because the bending radius and all, it will matter. So if you bend that cable, the losses will be more. So once if you routed that cable, no, say suppose from the controller room you are sending to the antenna like 1 dB or 10 dB signal, power signal, RF power. So how much it is reaching to the antenna? So you want to cross check that. So you want to compensate that losses, no. Say suppose your antenna requires 10 dB signal exactly, but your cable losses will be 2 dB. So you have to compensate that loss to get the accurate signal, communication signal. So to do that, we are having a long distance VNA methodology. Yeah.
So you have got the question. Okay. So, and you know about the time domain. You heard about a time domain. Time domain measurements. What you will tell the time domain? Okay. So what is the measurement you will get in the time domain?
I'm not sure what are the measurements like. We usually check for bandwidths like simple VSWR bandwidths, that kind of thing we check in time domain analysis for basic patch antennas.
So what will be the output in the VNA you will get? So you will be measuring what will be the x-axis and y-axis?
The x-axis would be probably time, and in log how much the gain is changing, or how much the reflection coefficient, how much the losses are coming.
So I think that is related to, you are telling about the spectrum
Yes.
oscilloscope.
No.
Oscilloscope the same thing, no? It will give the x-axis and the voltage.
Yes.
Frequency and the voltage, no?
Yes.
So you are telling it will be giving the time versus frequency.
Yeah.
Okay. And that will be the one trace what you told, and other trace will be the impedance. Okay. So when you want to do the time domain measurement, you want to do the impedance mismatch, you want to test in your DOT or in a CRT board, you can go for a time domain measurement where you will transmit the frequency and you will get the impedance in the x-axis. Where is there is a, suppose if we are tuning or there is any impedance mismatch in the circuit or any system, you can use a time domain and you can find out where is the impedance mismatch. In particular distance also you can find out at what distance we are getting the impedance mismatch kind of thing. Suppose we are transmitting at 50 ohms, in the center of that there will maybe a 75 ohms, or there is any twist on the cable, or is there any mismatch in the cable, we will get the impedance mismatch. To find that we will be using a time domain. Okay, so many of them will get confusion when you go for a time domain, they will think about oscilloscope. It is not an oscilloscope, it is in the VNA also there is a time domain axis. Okay, where it will be used to measure the impedance mismatch in the frequency axis. Okay. Okay, next we will go for the material measurements also. So what is the material measurement? It is a measurement which will be used to do the material measurement of the electromagnetic waves. Okay, using electromagnetic waves we will do the characterize the materials using electromagnetic waves properties of the material. We will test the electromagnetic properties of the material. So what are the objects depends on, it will be depends on the permeability, the magnetic field mu, and permittivity epsilon. So electric field. Okay, permeability is uniform throughout the frequency or the objects. So we will be not discuss more on the, or we will not do more testing on the permeability, but permeability will vary depending on the composition and environmental conditions and frequency. So we will be mostly concentrated on permittivity whenever you are doing the material measurements. Okay, so material measurements are based on permittivity rather than the permeability, because of it continuously changes depending on the frequency and the environmental conditions. So permittivity is a complex value where it will be involving the real and imaginary part both. So it will give the real part as epsilon dash and measures how much electrical energy is stored in the material, and imaginary part as loss factor. So it measures the how much energy is lost in the material, and the ratio between the real and imaginary is called as a loss tangent. So there are the different methods depending on the frequency range and the physical properties of the material and the desired speed and accuracy, and 4 more methods are there to do the material measurements. Okay, depending on the frequency range and the speed and accuracy of the material and the property of the material. So we will be using the transmission and reflection line method to do the material measurement, where we will keep the DUT between the 2 ports. Okay, and there is a coaxial probe method where it will be used for the liquid or a liquid material measurements. Okay, and there is a free space method where the material will be placed between the 2 horn antennas and we will do the dielectric property measurements. Okay, and there is a one more method, free space, one more resonant cavity method, where you will be doing the resonance method. We will be doing the resonance method where the DUT will be placed between the resonant cavity. So this is having some frequency limitations also. When you go for a coaxial, it works from 50 megahertz to 60 gigahertz, and transmission line 50 to 60 gigahertz, and parallel plate means it is nothing but resonance cavity method from 5 to 20 gigahertz, and free space is 5 to 500 plus gigahertz. So this is the coaxial probe method where we will be dipping the material or a probe inside the liquid and we will do the measurements. This will be done by using the one port calibration method actually. So you will be doing the one port calibration. Once after the calibration, we will connect directly we will dip the probe into the liquid and we will be measuring the properties of that. And when you go for a transmission line, we will insert it will be the permit electrical property. Yeah, we will provide a software and jig for this, but the VNA remains same. Okay, so we will provide the software and jig depending on the materials. So we are having tie-ups of some of the third vendor providers who will be material measurement they are doing. So we are having a tie-up with them. Using that, taking help of them, we will do the material measurements actually. Okay, and we will be doing the free space method where we will be connecting, as I told, between the 2 horn antennas. We will keep the material and we will do the material measurements. Okay, and resonant cavity and parallel plate method. So these all depends on, these are some of the tie-up vendors we will be depending on that for doing the material measurements. They will provide the software and the test jigs to do this material measurements, like Compass, Keycom, Swiss. Keycom, or they are expert in both resonant and non-resonant methods. So they will do the resonant method, means they will keep the DUT middle of this, and they will do the calibration before inserting the DUT, and they will take that as a reference, and once they connect the DUT, and they will do the measurement of all the 4 S parameters. Okay, circular method. These are some of the resonant. Non-resonant method means it is like a open coaxial probe method. They will do directly, they will dip into the liquid and they will do the property measurement of the properties, reflection and transmission both. So this is about the permittivity measurement. If there is a requirement of permeability also, we can do that. Okay, we will support for both permeability and permittivity both. So these e-compass, they are in non-resonant method, like free space method they will be doing, and they will be connecting the middle of there will be a 2 horn antennas. Between that horn antennas, we will keep the material and we will do the measurement of that. You can see this is the 2 horn antennas. The material will be placed between this and we will do the measurement. And this is the sum of the coaxial probe method, where we will be inserting the probe inside this and we will do this measurement. So it will be between these two. So this is the transmission line method, where we will be inserting the sample between these 2 ports, and the network consider one port will be connected and other port will be connected here, and we will do the material measurement of this DUT. So these are some of the examples. So this is the chamber kind of thing, the whatever the chamber, anechoic chamber, it will be placed between this material, and sometimes we will insert the horn antennas inside this chamber also, and we will do the material measurement if it is affecting from the radiation, outside radiation. Okay, it is furnace kind of thing. So these are some of the examples. You have any doubt in the VNA or anything?
Sir, what are the most common mistakes while engineers makes when using the VNA in practical insights or your real-time experience, real-world experience?
Okay. So mistakes means we will not tell as a mistake. We have to take a precautions whenever you are doing the measurements. Okay. So without knowing the, as I told previously, so VNA is used for the known signals. Okay. Before doing the measurement, you have to know what is the component you are doing measurement, and what are the parameters you want to do, and what is the frequency range of the instrument. Okay, and you want to check what is the power level. If it is active component, what is the power level it will be generated on that. That may damage your network analyzer or a testing instrument. Okay, so many end users will don't know the what is the power it will be generated in the active component. They will feed to the instrument, and they will damage the instrument itself directly. So this has to be taken care whenever you are feeding high power, when you are working with high power or active power measurements or power components. Okay, and one more thing we will suggest, whenever you are going for higher level or in any company or production or in R&D, better use the ESD mats to do the measurements or keep the instrument on the ESD mats. Take a precaution of ESD, electrostatic discharge, because this may damage your connectors or any cables or any inside the instruments also sometimes. Okay, because we cannot tell the ESD when it comes and when it discharges, kind of thing. And that's it.
Thank you.
So before doing any measurements or anything, please go through the device and what is the measurement you are doing, and just go through the measurements also and device characteristics, properties, kind of thing.
Sir, I have a doubt. I was heard that we have to take in proper care of the channel we are connecting, like the connection between the VNA and our antenna. So, what's the reason behind that?
So suppose if you are having an antenna of a N type, so N type connector will be different, and the connector of the network analyzer may be different. Suppose the connector of the network analyzer is a K type. Okay, so you cannot insert the directly K to N type, so you have to use an adapter. So whenever connecting the adapter, please take care of the connectors or connecting of the adapter. So you have to go through the connector kit training kind of thing. There is a website, in the website there will be available how to do the connections also. So there is some technique to do the connections also. If you do the mislead the connections kind of thing, or you put tightly, or you are putting your effort in doing the connections or rotating the cables or anything, it may damage the connector. Okay, and whenever you are going for the any net connectors, there is a difference between the connectors, each connectors. You have to know, we cannot meet a 1 point. Suppose you are taking of a 2.92 mm connector, we cannot mate with a 1.85 mm connector. But the inner dia will be different. Outer it will be similar, but the inner dia of the connector will be different. You cannot force it and you cannot meet that, or you cannot do the connection. It may damage the inner pin of the connector. Okay. So take care of that. Whenever you are connecting, always rotate the male connector. Don't rotate the female connectors. Okay.
Sir, and also we have to avoid bends on the cables we are connecting. So if we make a bend in the connectors, like the VNA to the cable when we have to avoid benders, right?
Yes.
If we make a bend, it will affect our result, or it may interfere our result.
So whenever you are connecting, the cable should be straight, and whenever you are using the cables, it should be phase matched cables, what we call. So phase matched cables will be having 180-degree phase match. Okay, so if you bend also, it will not flexible, it will be there. And use the genuine cables whenever you are doing the measurement if you need a more accuracy kind of thing. Okay, so if there is any bend or if there is any splice kind of thing, it will automatically, it will affect in your measurements also. Okay, you will not get more accurate, and amplitude level will be decreased automatically. So measurement whatever expected, you will not get the expected reading in the output of the network analyzer or the receiving end. Okay, it will drop the signal. So this parameter also can be tested in the VNA. Actually, there is a distance to fault measurement option in the VNA, some of the VNAs, where you can measure the length of the cable also. If it is cable is having somewhere around 50 meters, or where it will be connected. Example, where in the base station the control room will be one in the down, and then there will be a tower which will be antenna will be connected on the tower at the top of the tower. So the cable will be going from controller to tower, and we can test that cable with the antenna also. Okay, if there is any splinge or any cutting or any discontinuity between the cables, we can find it out using the distance to fault measurement option in the network analyzer. Okay, so we can test the cable as well as the antenna also. Anything else?
Sir, sir, in the case of material measurement inside the waveguide, you have shown in a slide. In that case, how we can calibrate the system? How do we calibrate the system?
So you will do the normal calibration. Suppose if you go for any method like coaxial probe method, so that will be the having the open-ended coaxial probe method. You will do the one port calibration at the end of the cable. Okay, and you will connect the test stick. Okay, and you will connect the test stick, and that one end, the open end of that cable, it will be going for the liquid or a methanol. You have to do the calibration using a water or a methanol, and you will take it that as a reference. And once you have taken that as a reference, you will connect, you will put a liquid kind of thing, whatever the material you want to measure, you can keep it there and you can do the measurement for a coaxial open ended method. For a transmission method, we will do the same similar thing. So you will do the calibration at the end of the cables, 2 port cables. Okay, and you will connect a horn antenna, and we will keep it that as a reference without connecting keeping the DUT between the 2 horn antennas. Okay, so you will do the calibration and you will keep it this as a reference. Once you inserted the material between these 2 horn antennas, we will do the measurement of that.
No, sir. In the case of waveguide.
Waveguide, it will be connected. When you go for a waveguide, it will be banded waveguide actually. Okay, it will work in different bands. So there is a separate waveguide calibration kit available in ANRITSU. Using that, we will connect the waveguide. We will do the calibration at the end of the waveguide. Okay, and after once we have done the calibration, we will connect the horn antennas in the same phase. Okay, and we will do the through calibration, what we call it as a through calibration. Once we connected with the face to face of the horn antennas, and once we have done the through calibration, we will insert the material or any thin film sheet between these 2 horn antennas, and we will measure the S parameters. Okay,
Thank you.
so we will use a SSLT or triple ST calibration method for that, for a waveguide. So let me do one thing. Can we show the instrument? Give me 5 minutes. I will show the instrument, how it works and how the Shockline software works, and I will show how the frequency will be setted and how you can use the VNA also. Okay, so you have used any for your network analyzers? So as you all used, no? Okay, so these are traces what we will see when you open the Shockline VNA. Okay, so you can see there is a 4 traces as we discussed. Okay, so you can see there is a 4 traces. So whenever you are doing the calibration, whenever you see the network analyzer, you want to set the frequency range. As I told, it can be set depending on the network analyzer frequency range or the device you want to measure. Suppose your device is having somewhere around 1 to 3 gigahertz or 1 to 4 gigahertz of the frequency range of your device, or any cables or any splitter kind of thing, there will be a frequency range of somewhere around 4 gigahertz. So you want to do the calibration up to what frequency you will do the calibration? You will do up to 4 gigahertz, or you will be doing the calibration up to the whatever the frequency is of range of instrument? What you will be doing? Suppose if you are having a frequency range of the cable is somewhere around 18 gigahertz and you are having a network analyzer up to 20 gigahertz, so you can do the calibration up to 20 gigahertz because the frequency range may exceed. Okay, so you can do up to the 20 gigahertz frequency range, and you have to set the start and stop frequency here, and you have to set a data points. Why you want to set a data points? What is the data points? It is a sampling of the trace. So if you set a more data points, you can do a more sampling and you will get a better accuracy and the resolution. When you are feeding a marker, you are setting a marker, you will get the particularly at particular point. It will increase the resolution also. So you can go up to 16,000 data points in the shock line VNA, whatever the software you are using in this. And if you go for a performance VNA, what I showed, the performance VNA, it can go up to 1 lakh data points or 25,000 data points per trace kind of thing. Okay, so this will be used for a sampling the data points. Whenever you are doing for the passive components, it is 501 and 1000 data points is sufficient because you are doing the passive components. Okay, and parallelly if you take a more data points, it will take a more time because it has to sample a more data points. Okay, so once you have set this start and stop frequency and the data points, you can set the calibration. So in the calibration, as I told, there will be a calibrate menu. In the calibrate menu, as I told, it will be having a auto cal or a manual cal. So auto cal will be works on the algorithm software. So just we have to connect the module between the two ports and we have to press auto cal. Okay, and when you go for the manual cal will be more accurate compared to the auto cal because that will be works on the software and this works on the calibration standards. Okay, so we can do the calibration either 2 port, 1 port, or transmission reference or a reflection frequency response. When you select a 2 port, it will cover all the 4 S parameters. Okay, full 2 port will cover all the 4 S parameters. When you do for the port 1 port calibration, it will covers only reflection parameter, then that will be done for only the 1 port, either port 1 or a port 2. Okay, so once we have done, you can go for a modulation modify cal setup. In this you can select the SOLT, SSLR, SYLR, SSLT. SSLT and SSST used for the waveguide calibration. Okay, and LRL and TRL, this has to be known. LRL means line reflection line. You have to know what is the electrical length of the line or reflection. It may be open or a short. You have to know this values, electrical length of this, and we can enter that values and we can do the calibrations. Okay, so now we will be doing most of the time for a 50 ohms or a coaxial, we will be doing the SOLT calibration. And this is the type we have to select, either you are doing for a coaxial or a non-dispersive waveguide or a microstrip. We have to select which is the DUT. Suppose if you are having a waveguide, you have to select a waveguide and you have to do the double SLT calibration or triple ST calibration. Okay, for coaxial we will do the SOLT calibration. Once you have done this one, we have to go for edit parameters and we have to select the what is the calibration kit you are using. Okay, there is a different types of calibration kits here. So if you select the particular calibration kit, suppose TFSL KF50A, so this data, whatever the cal coefficient of the standards, it will automatically enter to the memory of the instrument. So because the calibration kit also it is made up of a LC component, so there will be having some offset values. So once you select that particular model number of a calibration kit, it will automatically take care of that cal offset values in the calibration standards also. Okay, so we have to select all these port 1 and port 2 and you have to press OK. Okay, if you do all this, you will get a more accurate reading. Okay, so once you have done this one, you can go for a back and you can do the start the calibration. So you have to do for a port 1. So you will be connecting the port 1 cable, and you will be connecting open, short, load, and through, load, and you will be doing for a port 2 also, open, short, load, and we have to do a through. Through is nothing but the connecting a female to female connector of the calibration kit to the one end of port to the other end of the port. Okay, and we are doing the calibration. Once we done this one, you can just go for a back. Okay, so now this will be the display what you will be getting, and this you can select what is the trace required to you, and in this there is a display format. As I told, you can select a log magnitude for a trace one, or you can select a linear or a phase, or you can select a VSWR, or you can select the Smith chart, because this will be the reflection parameters which will be connected in. It can be done from the S11, or you can go for a S12, and you can select the group delay, or you can do the log magnitude value, group delay measurement, and phase measurement. So this all comes under the transmission parameters. Okay, you can select any traces with any parameters, and you can do the measurements. Suppose I want to do I will be doing this as a log magnitude, and I can put a markers up to, it supports up to 12 markers. You can select a 12 markers with a different frequency, and we can do the measurement. Suppose I am keeping this for a 550 kilohertz, I can keep it this for a 1 gigahertz. Like this, you can set up to 4 or 5 gigahertz. I can maximize this, and I can analyze what is the value of that particular frequencies. Okay, and as I told previously, you can go for an application here. There is a multiple source setup. In this we can do the mixer measurements also. Okay, you can set one as a LO and second port as a RF, and we can do the IF receiver measurements also for up conversion and down conversion. And suppose so if you want to do a de-embedding, as I told previously, you can do the de-embedding also. You can edit the de-embedding network. Like if you need a LC circuit, LCR, you can give the what is the inductance value or a capacitance value in the board, or resistance value, and you can add to the your network, and you can do the de-embedding. Okay, de-embedding means pulling the RLC component from the circuit. So you can edit this one. You have to enter what is the RLC value, and you can de-embed that and apply to all, or you can do the embedding also. Once you have done this one, you have to put the embedding on. Okay, so there is option of doing this de-embedding and embedding tools, and you can do the saving option. Just you can save the data of different setups, like you can do for a S2P file, CSV, bitmap, PNG format, everything. You can save the traces in the internal memory or the data desktop, and you can use for a post processing kind of thing. Okay, so suppose if you are doing the calibration at K type, N type VNA, N type the port of the VNA or a cable. So if you connect the adapter, K type adapter, where your DUT is a SMA or a 3.5 mm, usually the whatever the patch antennas you will be using now, that will be SMA or a 3.5 mm usually. So you have done the calibration at the N type connector or N type cable, and now you are connecting an adapter and you are doing the characterization of an antenna. So this adapter also adds to your measurement. So what you will do? Sorry, Okay. So there is a calibration kit of N type. So you have done the calibration at the end of the cable, N type cable, and now you are adding one more adapter K to N to do the characterization of the antenna, which is a K type antenna. So in that case, there is a option called frequency reference plane extension. Okay, using that reference plane extension, I can extend the length of the reference plane up to the end of the adapter directly. So I will connect the adapter to the port 1 and I will press the auto length and loss. So it will compensate the what is the electrical length of that adapter and what is the loss of the adapter. It will give the value of, take the value of that, and it will extend the reference plane up to the end of the adapter, and that will give the measurement of the antenna. Okay, there is a, this is the method what we will be using in the VNA. Okay, so this can be done. And is there any doubts in this, the VNA measurements, or in the software is there any missing kind of thing, or you want to know something? Whenever you are using a network analyzer, you are facing any issues or anything you want to know? We can do the save the setup also in S2P file, which will be compatible for a programming. Suppose you are doing any LabVIEW, MATLAB, C++ or a Python programming to the network analyzer, we will be providing a skippy commands to you. Okay, you can use a skippy commands and you can write your own programming. And if you want to extract the data, it will be having a S2P files which is compatible for all these programs. So you can save the file in S2P format and you can extract in the MATLAB, LabVIEW or in other programs. Okay. Anything else?
If we want to take the S2P file of a pin diode,
just you can go for a file here. In the all the instrument there will be having a, it will support for S2P files. Save the data. In this we have to select what is the file. Suppose S2P file, or it is a 2-port device, you have to go for S2P, and it is a single port, you can select S1P. Just you have to save the file in wherever it is required to you. You can save it in pen drive or in a desktop, and you can extract the data. After that you can extract the data. Okay, usually when we are doing the softwares also, we will take the fetch the data S2P file itself. Whenever you are doing the radiation pattern measurement or any test fixture like any material measurements, we will fetch the data S2P file and we will convert to the whatever the further processing kind of thing. In the radiation pattern also we will fetch the S2P file and we will plot the radiation pattern S21. Okay. Anything else? Yes.
Network analyzer. Some of them have used it. So in case of any doubts you have, please check with me. Right?
You can always welcome for any doubts or anything. Madam will be having my number and I will share her the visiting card of so you can just share you can ask any doubts in the over the phone, or you can send a mail to me. Okay, I will reply to that. Okay, thank you for your time.
Okay. Thank you, sir, for such comprehensive and interactive session. The practical insight you shared will undoubtedly benefit all participants. So, before we conclude the session, we'd like to take a moment to express our gratitude to our distinguished speaker for sharing valuable insight with us. We now invite Sri Lakshmi Narayan T to kindly accept a token of appreciation as a small gesture of thanks. I request our beloved Deepthi ma'am to do the honor.
Thank you all for being part of such an engaging and insightful session. We hope you found the session so far to be enriching. And